dense methods are very practical, very easy to use, but they generalize quite poorly and they have a lot of edge cases. That's inspired by all of this. So the idea is we encode a document exactly like how we would with a dense embedder, but we remove the pooling mechanism. You just give the PDF to it and then you can query it. Okay, so after I told this, RAG is more than dense embeddings because Jason's got a blog post that's called RAG is more than embeddings, which kind of focuses on the very product-oriented stuff. And I'm going to give a more like retrieval model / research view on this. And so RAG is more than dense embeddings. If you don't know what a dense embedding is, I'll define that in a second. If you do know, you probably do know what I mean. So first thing about me, I do research and development at Answer.ai under Jeremy Howard, who you probably know for FastAI, and a bunch of other like really cool people. My background's mostly NLP and retrieval, mostly legal retrieval. I'm only famous on Twitter really for Ragatouille and rerankers, which are basically libraries to make respectively Colbert and re-ranking models easy to use. If you don't know what Colbert is, this is the right talk because that's like half the slides. And I'm pretty unwell today, so sorry if I'm like slurring a bit, etc. Like the brain fog's not amazing. I'll try and make it as clear as I can. And with that being said, the agenda is a mini reminder of what dense embeddings are. Then a small section on lexical retrieval, which is basically the ancestor of semantic retrieval, but also something that is very, very relevant today. And we're going to see like a quick example of why. This is something that's been covered before, so it shouldn't be that new. Then it's beyond dense embeddings with multi-vector methods, Colbert, and that will not be brief, that's half the thing. Then Colpali, which is something I'm very excited about, which will make more sense once you know what Colbert is, but brings Colbert to images. And then there's cut content, but I might share like my fuller version of the slides later, which was about 2-stage pipelines and how re-rankers work and how you can make your re-ranker work really well with your first stage model. This is just a teaser. I promise there's no slide on this here. Yeah, with that said, dense embeddings. So dense embeddings are called dense because they're a single vector and that vector is dense. That means you've got 1,000 dimensions, 768 dimensions, and every single one of them is a full floating point number, the full integer. If you've quantized it, it's like that vector is a full vector. And that is mostly, I'll say, a pedantic distinction nowadays, because when you see them referred to in just about any blog post or anything, they're just called embeddings. When people say embedding search, vector search, they mean dense embeddings. It's nearly always what this means. Basically, the act of turning text into a single vector or an image into a single vector is creating a dense embedding. There's lots of pros to this. They're very simple to use and get started with. I think you've all seen the sentence transformer example. You've all done RAG. You know how easy it is to just text in, vector out. That's simple. They have a low storage footprint. They're very intuitive. It's quite easy to be like, okay, so these numbers capture the semantic meaning of your document. And that's why they're everywhere. That's why you use them. That's why they're so powerful for RAG. And I won't cover everything here because obviously you know what they are probably if you're taking this course, and they've been discussed a lot. So what I will talk about a bit more here are the shortcomings. Why do they fail? Why am I even advocating for other methods here? And one of them is that they're very powerful, like I said, but they're also given a completely impossible task because you're asking them to compress information from hundreds of tokens or even thousands of tokens if you're doing long context into a single vector. And what that means is even if you have, I don't know, 1,000 floats, 3,000 floats, you're not going to capture the full meaning of the document. There's going to be some information loss. At some point, you're going to miss out on something. And what you're going to miss out on is going to be extremely influenced by the pre-training of your model, because what will teach the model what information it should keep, because compression is basically the act of choosing what you keep, choosing what you see as representative, and what will be representative, what will be kept by the model is something that will be relevant to the training queries. So your single vector is extremely influenced by this. And what that means is that it will probably not match your data. And Jason's a huge advocate for fine-tuning. And that's why, because if you don't fine-tune your model, that aggressive compression will result in information loss, which will result in information loss for your specific use case. And you will also nearly always lose fine-grained details. And I have an example on that in a couple slides. So I have taken a slide that you might remember here with permission from Joe Bergam, which is the missing baseline called BM25, more on that in a second, which is just statistical analysis of your data. Costs very little to index. There's no models. It's very limited. It's something that you should be doing. It's something that people often don't report in their papers because it's so good that it makes your very computationally expensive method look a lot worse when TF-IDF does so well. And so the first question is, why is it called BM25? And it's because it took the authors 25 tries to get it to work. Like there is a series of methods called BM1, BM2, up until BM25, which produced good results, and BM26 was worse. So they decided it's best match 25. It's our 25th approach at making this work. We've been using that name since the 70s, so they did well. It's what it is don't really matter. If you're familiar with NLP, you will know what TF-IDF mean, which is term frequency, inverse document frequency. All you really need to know in practice, because those are scary words, is that it's term weighting. So it's going to look at your entire corpus of documents and look at every single word that ever gets mentioned there, and it will basically rank them by importance based on how unique they are. And then when you query the documents, you will type in a query which will have a lot of keywords in it. And it's going to just try and find those keywords in the documents and see which ones have the highest weighted relevance score. This works really well because we really love keywords. If you ever taken a look at your user queries, you will see that, I don't know if it's a natural human behavior or if we've been Google trained from birth to the point where now we kind of type with keywords, like we're always going to use one or two. So you should always ensure you've got some sort of lexical approach built into your pipeline. And that's one of the most common representation methods that kind of gets a lot less publicity than pure methods, but it's very useful. And a good example as to why it's very useful, why you should use it, even if you've got the world's best embedding model, is this situation. So let's say your query is, what's the ULEZ Texas shop profit for FY24? So you've got a lot of keyword in that sentence, which is ULEZ Texas and FY24. But then you've got two documents or 100 of documents, it doesn't matter. One of them is Houston, Texas FY23 profit, and one is ULEZ Texas FY24 profit. They both have content. We don't care about the content here, but to a semantic model to your embedders, those Houston, Texas FY23 and ULEZ Texas FY24 are virtually the same text. Both of those titles will score 99 point something for your query because semantically they are virtually the same. ULEZ is a suburb of Houston, FY23 it's FY followed by a number. This looks identical to BERT or to an embedding model. However, to BM25 or to any form of lexical matching, this looks extremely different because the score for FY24 in the first one is 0 and the score for FY24 in the second one is very, very high. And likewise for ULEZ and Houston. So lexical matching is something you want to have just to handle those simple cases. It will often come up, not necessarily in this easier form, but it costs virtually nothing to add to your pipeline. So why not? This is what I mentioned earlier. This is from the Bear paper, and Bear is probably best known as the retrieval part of the MTEB. So if you ever check the MTEB leaderboard, that is this benchmark. And on the original paper, they included a bunch of fairly heavy-duty transformers-based models. And you can see that PM25 for something that came up in the 70s is remarkably good and gets better as you go to longer documents because the more tokens you have, well, the more words you have in your document, the easier it will be to match at least one keyword. And this is the first of two academic tables in this, and I do apologize. I know LaTeX don't look amazing, but it's useful. And then a quick word. This is a section where I had to cut quite a bit, but something that's you will also come across or might have heard of, so I thought I would mention it quickly, is SPLADE. And SPLADE is a neural network-based approach, like dense embeddings, but it learns sparse representation because it's basically using Benny transformer, but most commonly BERT, to create sparse representations. And what the transformer does is provide it with an expansion mechanism, so it's able to infer relevant vocabulary, which is not actually in your query, but has strong overlap with your query. And so it avoids cases like this one, which is if you take our example before with FY23 and FY24, or FY24, sorry, twice, but one time you go FY24 with a space in it, and the other you have FY24 all attached. For BM25, those are two different tokens. So FY space 24 has a similarity score of 0 with FY24. SPLADE has a learned expansion mechanism where it kind of will learn this overlap, and this is an example from the paper, the screenshot here, where for BM25, Indonesia question mark is entirely different from Indonesia no question mark. And this happens a lot. So SPLADE is basically why if we use the fact that transformers contextualize token representations to expand on our terms and create BM25++. This means that it captures some semantic content, but it's not very good at actually understanding meaning. So sparse methods, be it BM25 or SPLADE, are not something that you're meant to use on their own. If you include them in your pipeline, it should be either as a first stage model to then re-rank documents or to use in conjunction with embeddings to do what we call hybrid search. And Joe mentioned this, where you will just combine the score of your cosine similarity with embeddings with the score of SPLADE or BM25 to create like sparse dense representations, which works pretty well in a lot of cases. Like it's one of the things that you see all the time in the literature. And that is the end of likely this intro section on the two things that I was going to talk about without really talking about, Colbert and late interaction. So if you've heard of me, you know that I love Colbert. I think it's a great idea. I think everyone should use Colbert. It does have trade-offs. I'll cover them. The other thing, and that's one of the many reasons why it's obscure, at least up until relatively recently, is that it has many, many names. The main mechanism is called multi-vector representations. So if you see multi-vector somewhere, it's Colbert, and that's because it uses multiple vectors to represent documents. You will also read late interaction model, and I'll try and explain this, but it's basically because it keeps both query and document tokens so that they interact at the latest possible time, as in the only time where they will actually interact with each other before being modified is at the very end when you score them. When you do normal dense embeddings, they don't have this late interaction because they've been pulled a long time ago, like they've been turned into a single vector, so the tokens are never aware of each other. Whereas when you use Colbert, they do meet each other at the end at scoring time, which is why it's called late interaction. It's not the most intuitive name, but you'll probably, if you use it, you'll probably come to see how that works. And then there's a why Colbert, like we have lexical representation, we've got sparse models, we've got dense embedding that captures semantic relationships. Why do we need this? Why do we need a new method? And it's essentially because all the methods that exist have drawbacks. So sparse methods, they're very strong at keyword search. Like they'll find the keywords, they'll match like obvious terms. They're not very good at any sort of semantic relationship. Like they will not really understand the meaning of a document. That's not what they're here for. Dense methods are very practical, very easy to use, but they generalize quite poorly and they have a lot of edge cases and they'll never be perfect because there's just so much compression. And then the other thing is re-ranking methods, so like cross encoders, which is essentially you give the same model, the document and the query together. So it gives a score for this document query pair, are very powerful and they're always the best scoring on benchmarks. But the problem is you need to run it for every single query document pair. So that's one model in France for each candidate. So if you have 1 million documents, you cannot do that. And so Colbert is inspired by all of this. So the idea is we encode a document exactly like how we would with a dense embedder, but we remove the pooling mechanism. So like instead of putting it all into a single vector, if your document has 500 vectors, then 500 tokens, your Colbert output will have 500 vectors. This obviously is costly in terms of storage, and we do have ways to alleviate that. But the first thing we do is add a downcasting layer, and that's been studied quite a lot. You can comfortably even turn down 1,000 dimension vector into 128 or even 96, and that will still work because while the vector itself is really small, its only job is you have to represent this one token. So the task is much easier. So that also gets learned in training. And the output is that every Colbert represented document is a bag of vectors. So if you have 300 tokens, you have 300 vectors, and that will make scoring much easier. And how do we score this? So it's always cosine similarity. Every time you need to score something, it comes down to cosine similarity. We hate it, but we don't have anything better than that. And more precisely, Colbert uses maxim, which stands for maximum similarity. And that is for each query token, we'll compute its cosine similarity with every document token. Then for each of those similarities, we'll keep the highest one, which is the maximum part. And then we will sum all of those token level maximum scores. So the final score for the query document relevance is the score of that sum. And in practice, it looks like this. These both happen at separate times, like the encoders are completely separate. They meet very late in the maximum operator, and we would put a single similarity score at the end. I wasn't very clear about that, but the lower dimension projection is just a single linear layer at the end of the network. The way you would add a classification head or a pooling head, we just add a single head at the end that does like 768 if you're using BERT to 128, and that they're doing training. And that can be added to basically any embedder. Like you can train for about half an hour to turn any embedding model into a Colbert model because all you really need to learn is that projection. The other thing there is storing so many tokens does seem quite impractical, and it is, because if you have 512 tokens in your documents, then you have to store 512 vectors, which is 500 times more than if you stored one vector. This is pretty simple math, and it does not look good for us. But the good part of that is we do have the downcasting layer, so those vectors are much smaller. Then the second one is aggressive quantization. That's actually quantization Quantization's become a hot topic now, but Colbert since 2021 has been quantizing to just 2 bits. And that is because when you're doing token level representations, it's pretty easy to actually delegate a lot of the token information to a residual that will like kind of represent this family of tokens. And then you only have to store 2 bits for the actual document, for the actual token representation. And there's also recent work from us, which has shown that you can perform small scale pooling. So instead of doing the whole, like everything into a single vector, like you would in a normal dense embedder, you pull tokens 2 by 2 or 4 by 4, and you manage to keep most of the local information still, but like reduce storage by up to 75% without really losing any retrieval performance. And I'll get to that at the end, Jason, because we do have VectorDB support now, but the answer is Quadrant in Weaviate and LansDB if you want to use it as a re-ranker. And so this is kind of what it looks like. At the start, it's terrifying because you only got 300 tokens and somehow it's 3 megabytes or 3.6 megabytes. You're not going to do that. With dimension reduction, you're already down to 0.6 megabytes, which is not great, but you can do it. And if you introduce pooling and then 2-bit quantization, you end up with around kilobytes per document, which becomes quite accessible. It's a third of 1024 single vector would take. So this is much more heavy-handed, but you can do it. It's the message here. And how does Colbert fare in the real world? That's a question because I think we all know, or we all learn at some point, that there's a massive difference between an academic paper and something looking good in a paper and then something looking good in your pipeline because it's easy to overfit on benchmarks, etc. And Colbert's been a weird paradox because it's been a favorite at all IR conferences. There's like around 5 to 15 papers talking about Colbert, studying parts of it at like SIG-IR every year. And it's been very strongly adopted by like search startups, like Algolia uses Colbert internally a lot, things like that. But up until earlier this year, very few people were using it. And that's mostly because it suffered from usability issues. The original repository worked, but was really not friendly to use in any sort of production setting. And all the reproductions were equally academic code. So nobody was really interested in putting it into production, except people who are making money putting it into production. So they were interested in other people being able to do it. So you kind of had this, if you know, you know, and if you don't, then we're happy you don't because we're making more money. Because earlier this year, there's been Ragatui from me, and there's been Vespa having a strong Colbert push. So adoption went up a lot. Weaviate is about to release Colbert support. I think it's due this month, actually, late in September. Quadrant has Colbert support. LansDB integrates Colbert as a re-ranker. So it's not ideal because you still need a first stage retriever, but you can try it out. There's a new backend framework named Pilate, which introduces a local VectorDB-like thing where you can create an index in memory for about 5 documents. This will be in Ragatui Lite in a couple of weeks, so it will be an even easier way to try it. So we're making progress on usability. The Colbert V2 model, which is now 4 years old, so it's basically an antique in machine learning terms, went from, I think, 50,000 downloads in January to now 4 to 5 million a month on Hugging Face. It's actually the most downloaded retrieval model right now, which is quite cool. So Colbert is seeing a lot of adoption because there's been a lot of recent activity, which has made it like both more practical and more performant. And that shows with the model we released recently at Answer.ai, which is only 33 million parameters, but basically beats all existing mini models on the bare benchmark and even out of the main benchmark, and is competitive with even large variants. Like it's better than E5 large on all benchmarks. So do give it a try as a re-ranker. If you're using LansDB, it's just a single thing to add at the end. You can use it by using Colbert Ranker, I think it's called. And this really cool thing, which I think Joe briefly mentioned in this talk, but it did not praise it enough, is that Colbert also does long context without needing trained for it. And this part's a bit misleading because the only way to use this right now is Vespa because nobody has a public implementation of it. But since Colbert works at the token level, what the Vespa team does when you're trying to embed a really long document is basically apply a sliding window to the encoder and stores 8,000 tokens if needed for a given document, then does maxim over those. And that is basically state of the art for long document retrieval, at least on a few benchmarks, and it does a lot better on M3 or even like LLM-based embedders. So that has been really amazing work done by the Vespa team and done by Joe himself. And this real world thing is something I want to segue into Colpali because Colpali or Colpali, I'm still not sure how to pronounce it. The whole team's French, so we all say it with a French accent, which doesn't help. It's a very, very recent development, which is basically a month old, and it uses Colbert, like the late interaction approach, to image tokens. So if you've been following what's been happening, people are really bullish on vision language models. So LLMs that look at images, look at videos, and treat an image or a video token as just a token. So it's, for us, when the model is encoded it's just a token, meaning you can manipulate it like a token. And that idea is a massive step towards document understanding pipelines, very simple ones, like for proof of concepts in less than 10 minutes. And so right now, if you're processing documents, you are applying retrieval to documents in a really extensive pre-processing, heavy-handed way. You're probably using unstructured or a similar thing. And that's a lot of steps. Like you have to OCR to extract the text, you have to clean up the output. If there are images, how do you represent them? Do you get an LLM to describe them? So we do like textual retrieval. Do you use clip embeddings? If you've got tables, how do you represent a table? Generally, I think most people would give it to an LLM and be like, please, for the love of God, give me a very accurate description of what this table is so the user can query it. It's a lot of steps that can break. And more importantly, and it's something I don't like, it takes quite a while to go from 0 to 0.1, and 0.1 is really where you want to test things. And you will often need some custom components, which is even slower. The other way people try to do it is that embedding documents as images is not a new thing. We've had Clip for a few years, and more recently we've had Clip, and those are basically just a way to embed images into a single vector. But like we were discussing earlier, single vectors compress everything, and it can work okay to compress text because ultimately text is not that information dense at the token level, at least. But images are, because, so imagine it, if you're doing text in a single vector, you need to represent the text. If you're doing a page in a single vector, you need to represent exactly where on the page the text is, what formatting is used, what the table looks like, what the image looks like, and that has to all fit into one vector, even if there are 3 images, 1 table, and 2 paragraphs. So in practice, all the retrieval methods on documents showed strong information loss. And that's kind of sad because vision language models can read. Like it's been shown, if you use Sonnet 3.5, Haiku, GPT-4o, Qwen2 VL now, they're very good at reasoning across a document that you give them as an image. So that means that they can understand the content. What's sad is that if we try to use that understanding as an embedding, it doesn't work. Like it always does poorly. And the Colpali team tried a lot of things and it always did poorly. And their theory was basically that the degradation is just too much to overcome. If you try to do it single vector, it's not going to work. And they just kind of had a thing one day, but they were like, yeah, but Colbert works at the token level, so maybe we can do image tokens as the output. And it worked really well. So that's the second academic table. All the ones in blue are the output of pre-processing the documents, like putting your PDF through unstructured, some OCR, some captioning for the images and tables. In orange, you've got single vector image embeddings. And then in green, you've got Colpali, which again, Colpali has no pre-processing step whatsoever. You just give the PDF to it and then you can query it. And what's really interesting is it does really well across every single benchmark they tried. So it does well if you ask archive questions, but it also does well on financial reports or medical reports. So VLMs can read and Colpali can use that reading to query documents. But then the question you might have is in the wrong slide. So I'll change what I'm saying. The way it works is every part of the document. So when you're using a VLM, it creates patches. If you're using Colpali, it's 28 by 28. And so you have to put 28 pixels by 28 pixels. And we store a single vector for each of those. And then when you query the document, it allows you to do like very powerful scoring against those patches. So here, if you're asking which hour of the day is overall electricity generation, the generation thing will match some aspects of the query. And here we see what matched the hour token, which is this part of the document. So we can see exactly all the hours being represented. And this is what brought up this document as being relevant to this query. And then the last step, because we're doing retrieval augmented generation, so you need some sort of generation. And a question that I think people have with Colpali a lot is you need to still extract information. Like, okay, it's cool that you can do retrieval on images, but then what do you do with your LLM? It takes text as input. And I've been finding, and a lot of people have been finding, that the newer VLMs are very, very good at reading. They fully understand pages. So if you're doing a proof of concept, all you need to do is embed your PDF and then literally pass an image version of that PDF to your VLM in context. And you can ask your query as normal and be like, use this provided context. And the context just happens to be document token instead of text tokens. But to the model, it's the same. And then, yeah, it answers your query based on that. That's as simple as it is. We had a use case recently where we were working with people who wanted to query a 600-page documents, and getting the like production ready Visio for them to try took about 20 minutes, embedding time included, and passing it to Claude, since we had absolutely nothing to do to the PDF except embedding it once. There is some issues with Colpali, which is that right now the storage is around 2 megabytes per page. So they are working on reducing that. This is very much a V1, but it's a very promising approach. And I think it's likely the future of document understanding. And yeah, these are all the resources I mentioned. If you want to refer to them at the end, a lot of papers, a lot of libraries, and a small Colpali section. And yeah, thank you for humoring my propaganda. Sorry for the brain fog. And I also want to stress, because a lot of the time people take one extreme view or the other, as in dense vectors are useless or other models are too complicated, so I'm sticking to dense vectors. And I think neither of those are true. I think multi-vector is better, but I think you're still better off starting with something off the shelf like nomic embeds or BG embeds if you want to try something really quick. And basically, like Jason likes to say, don't fix what isn't broken. Start with a simple pipeline, see what is broken, and then improve on that.